So last time we were talking about some molecular modeling stuff related to the bonded energy terms. I said to make the molecules alive, we need to apply something to them. What do we need to apply?
Force field, sir.
Yeah, so we apply force fields, and force field it includes the two things: potential energy functional form and the different parameters. So depending on if there is any variation in the functional form or parameters or both, so basically you are using a different force field. So I said this is one of the type of force field, amber force field, and it has stuff related to the bonded interaction and non-bonded interaction. So, and I mentioned that there are both variable terms and the constant terms. So, constant terms, every force field within the software, some database will be there inside. So, for example, for if you want to calculate bond stretching related to energy, so you can see something related with the equilibrium bond length and some stuff related to force constant. So, if I ask you this question, like in the dihedral energy term, like what is the variable you are having? Suppose you look for the third equation. What is the variable you are having? Phi. Okay, and the other thing, K phi and phi 0, it should be considered as constant terms. In the electrostatic interactions, what is the variable? Rij. Okay, the distance between two atoms, I and J, so that is the variable, and the other things are constant, like the Qi, Qj, epsilon 0, these kind of things are constant. Okay, so I said these first three terms, maybe the third term is little bit involved, but this one also they are not, they are simple one. So we'll today focus on this term, which is related with the van der Waals interactions. Okay, so if you see all these equations we have talked about, and I said non-bonded are mainly the two things: electrostatic interactions and van der Waals interactions. Okay. For electrostatic interaction also I made it clear that the charges they could be positive or negative or like sometimes both of them will be having same charge, so there will be repulsion. Both of them having different charge, so attraction. So in the same way, you can see if there is a positive change in the potential energy, means it is unfavorable, and negative change in the potential energy means it is favorable. So it's attractive interactions. Okay. So suppose in the same way, now if you want to understand the Waals interactions. Now, anyone of you has exact idea, you might have heard about this van der Waals energy, but what is exactly the van der Waals energy? What is exactly van der Waals interaction? What is its difference compared to the electrostatic interactions? Now, I hope you are understanding. Like, we want to make the molecules alive. So, suppose in a system, if we are keeping any number of molecules, so they should recognize the other molecule properly. So, recognize means they should interact with them properly. So, bonded energy terms, we have given them properly. So, whatever energy changes has to happen if something else comes closer to it. So, accordingly, there will be change in the shape, and accordingly, the changes in the energy will be happening. Same thing, how the other thing is going to impact electrostatically, and again same thing like as per the van der Waals. So when something is going to come in contact with other, like we have seen the impact of electrostatic interaction. If something is having the charge Qi and the other molecule with charge Qj is coming closer to it, so how the things will vary, this can be understand graphically also and by the equations also. So same things mathematically and graphically we will try to understand. But before that, like exactly what is van der Waals energy? You know what you have learned.
So,
What is
like,
the
I think it's electrostatic is when there are permanent charges on the atoms or molecules.
okay?
But when we consider van der Waals, we consider temporary dipoles that are formed when two molecules come closer to each other.
Okay. So this is what we should consider as the main difference. Like there are, if two, like for suppose if I ask you this question, what exactly is van der Waals interaction, and like suppose take example of there are two methane molecules, like one of, like you can consider CH4 and another is CH4. And these two things, if you see them, like ions, what we said, they are having suppose positive ions with +1 charge or negative ions with -1 charge. So how they are going to interact, this can be understood electrostatically. But whenever there is some kind of interaction, always some kind of positive and negative stuff should come into picture, right? Like two things which are neutral, what kind of interaction they will be having. So in the same way, like when we are saying we are talking about ions, so we could talk about some kind of electrostatic interaction based on their charges Qi, Qj. But now it comes like these are called as so many times whenever they are having some charges, so some kind of polar kind of things you can understand. They are having some well developed charges, but there are so many molecules. They are, if you see, they are neutral only. Their overall charge, like ions, they won't be having plus or minus charge. They will be neutral only. So how these two neutral things are going to interact with each other? So there should be some positive and negative stuff, then only they are going to interact. So like if you take example of simple methane molecule, or even if you take example of water molecules or any other bigger stuff. So they still interact. Theoretically, at least they know that these molecules have their own interactions. But if there is no positive and negative, so then how the interactions are coming into picture? So something definitely there should be something positive and negative. So whenever we talk about, now we are not talking about bonded interactions, we are only talking about the non-bonded interactions like electrostatic. So you can consider the non-bonded interactions whenever you are having, they are always actually electrostatic interactions only. Now we can have so many different names for such interactions. Whenever you, if you go, if you are a molecular modeler and if you are going into depth of these interactions, ultimately you will find out that everything is nothing but some kind of positive, negative interactions are there. And then everything is nothing but electrostatic interaction. But for some uh, making the things clear, certain examples have been explained in somewhat different way. So we always do not have the ions kind of interaction, but we certain times have interaction between certain times non-polar molecules also, like methane. They do not have any like actual ion-like charges. So what exactly happens there? So I said everything is nothing but electrostatic, but people have made the subparts of this. Like electrostatic is the main thing, but then along with that, van der Waals interactions also people distinguish. Then there are other things also, like hydrogen bonding. Also, you might have heard. This is also nothing but one type of interaction. Then there are other things also. If you go at the levels of protein and stuff, again, people will be talking about this hydrophobic interactions. Always, these are nothing but everything is nothing but in terms of energies you can talk, with different variation comes. Sometimes bonding, sometimes interactions. When there is a stuff called as hydrophobic effect, then also this is also related with the energy, but with slight variation. But if I said if you vary, if you see everything, they are nothing but electrostatic only, and you can maybe you can subdivide into two parts. One is the electrostatic. Then if you want to make it specialized, you can divide into van der Waals, and if you want to make it further refined, you can just do so many variations of this. So what in our force field we have learned, there are different types of force field, and different force field might be having different formulas. Now in our basically what that particular force field we are talking about, we are having formula for electrostatic and van der Waals interaction. We are focusing on these two, but there could be formula separately for hydrogen bonding. There could be formula separately for this kind of hydrophobic interactions also. So these van der Waals interactions are the special case of electrostatic interaction, and they are dependent on something called as permanent and induced dipoles. Instead of ions, we can say we are talking about the dipoles. And when you are basically dipoles also, when you are considering, they are into two categories, permanent and induced. So based on that, again the van der Waals interaction can be divided into three different parts. One is the permanent dipole-dipole interaction, another one is the dipole induced dipole interaction, and the third one is induced dipole interaction. So I guess most of you should be aware of this term. What is exactly a dipole? Okay. Suppose if you don't know, just focus here that not like most of the molecules, they will not carry any net charge, but they will be always having some kind of dipole. Like for example, if you take example of this HCl molecule, so like here the chlorine molecule, chlorine atom is pulling the hydrogen's electrons towards itself. So some kind of electronegativity, electropositivity is there, and the chlorine atom is pulling the hydrogen atom. So there is some kind of direction along which there is some kind of pull is happening for the electrons, and this particular direction wherever there is there, it will be having some magnitude and also the direction, and this we are calling it as some kind of dipole moment. So if you take example of any of the neutral molecule, like here two molecules are shown, one is the CO2 molecule, another is the water molecule. Take any of the molecules, they will be always having some kind of dipole moment associated between the different bonds they are having, but certain times even the dipole moment can be cancelled out. So that if you take example of CO2 molecule, so you can always see like the carbon will be here the electropositive, the oxygen will be electronegative. So some kind of dipole moment like HCl will be there. But what is going to happen in this particular case, that for the other bond, the dipole moment, it will be exactly same and it will be cancelled out. So there is actually no net dipole moment. So there are this kind of molecules, what we call this kind of molecules as non-polar molecule. Okay. And if you take example of something like water molecules, so if you take example of this OH, there will be some dipole moment, but it will be like you can divide the entire molecule. If you cut down it into two parts, there will be some positivity on this side and some negativity on this particular side. So you can say that the molecule has been polarized. Okay, it is actually having two different parts. The dipole moment here, like compared to the CO2 molecule, it is not getting cancelled out. So you are always having some kind of uh, pull towards one another direction. So you can see here from the positive to negative side, there is some kind of polarization. So if some molecule, some other molecule, if it is coming in contact with CO2, it will maybe act almost in the same way whether it comes in contact from this direction or this direction. But if you take example of this water molecule, if some molecule is coming in contact from this side and this particular side, it will behave differently. Okay, so there is, you can say this is the net dipole moment I'm having, and these kind of molecules like water, they are having some, they are polar molecules, they are having some polarization. So when we are talking about our van der Waals interaction, you should know that this kind of dipole can be there, and dipole you can consider that it is like a something like a some partly positive and partly negative part the same molecule is having. Same molecule is somewhat partly negative and partly positive. Whereas when you are having ions, so it is either positive or negative. It is completely positive or completely negative, whereas dipole, it is something which is partly negative or it is partly positive. So this is what we can categorize our different electrostatic interactions and the van der Waals interaction. So if you focus on the first thing, which is dipole-dipole interaction. Now can you give me example of dipole-dipole interaction between which two kind of molecules the dipole-dipole interaction can occur? Okay. If you take example of two water molecules, so I said in the water molecules already there is well developed polarized part is there. So we are having some dipole movement which is going to have some net dipole moment direction. So if any of these molecules, then you can represent like this, that either they are having on one side they are positive, another side they are negative. So any of these two molecules are coming together, so their interaction will be like magnets. So whenever the negative end of one thing is coming in contact with positive, so then there are going to be the interaction. But are they going to held together or not? It will dependent on what system it is. Like these, you might be knowing van der Waals interactions are the weakest kind of interaction. Okay, but there are also, we have seen, these are three variations. So each of them having their its own strength. So dipole-dipole interaction should be considered as the maybe the van der Waals interaction with the highest strength, because the positive and negative things are already well developed. There are permanent dipoles. So this kind of interaction you can consider between two water molecules. It can happen. Like both of them are having the dipoles. Now you know that between the two water molecules, what kind of interactions do you always know that happens? There is hydrogen bonding. So what actually you might be knowing, right? Between the two water molecules, so that take it. So this oxygen and the hydrogen of another water molecule, not the same molecule. So this we called as hydrogen bond. So this is also, you can consider as it is nothing but what? It is dipole-dipole interaction. The hydrogen bonding is a special case of van der Waals interaction only. Okay. Certain times people might think it also as the electrostatic interaction, because people have actually defined these things in a such a way. In our formula, we do not have any special component for the electrostatic interaction, right? We are just going to take care of those things by simply based on our epsilon and sigma parameter. So this is about the water mode. Now suppose there is a non-polar molecule like CO2 is there and water molecule. So can the two things interact? Like if there is a one molecule which is polar, another molecule is non-polar. So ideally you can say non-polar molecules are some things which are like zero, and the polar molecules, okay, you can say sometimes one part is positive and negative. So how the two things are interacting with each other. So the theoretically people know. Now I'm saying theoretically, like certain things maybe cannot experimentally study directly, but whatever value, the overall value you get, something remains. Then something remains, so then you have to conceptualize it. Like, um, okay, I think I won't go to that level, but yeah, maybe just consider our comics related stuff. You always have these days in the Marvel, it is coming, the multiverse, when the teaches the function I talked about. So why the concept of multiverse will come? Because maybe certain things are there which might not be satisfied at the level of your universe, what is being your present. So certain things cannot be proved. So people then go and they cross the boundary and they say, okay, certain things can be satisfied from the other universes. That's why maybe there is a concept of multiverse, even though this is theorized only. Nobody knows, even we do not know the ends of our own universe. But these kind of things are theorized. So same things I talked in terms of when we talked about our energy terms also. I said in energy terms, bonded energy and other things, bonded, angle, dihedral, electrostatic, and the van der Waals interaction we talk about. I said when we talked about dihedral formula, I said this is not something some actual uh, uh, by which actual process these values have been, the formula has been considered, but this is like the out of the remaining terms, like some experimental studies will be there which will talk about the total energy, and then based on the bonded energy terms, angular, electrostatic, and van der Waals thing, maybe certain things values will come into picture. So this final energy, what you know total in experimentally, this will be balanced out with this dihedral energy term. So what is the amplitude value? I said like a term will be there. This will be coming into picture from based on what actually remains. So same thing will be happening at the levels of this van der Waals interactions also. Maybe certain experimental thing will be there that will be talking about some overall van der Waals energy term, and you know certain things are there, maybe dipole-dipole interactions can be measured very accurately, but certain things might not be able to, we might not be able to measure. So these kind of things will be theorized, and based on theory to match this total energy, some values will come into picture. So this kind of induced dipole also you can consider, like these are theoretical things, like where actually we know that non-polar molecules do not have their own dipole moment. But how it is theorized, you can consider like even though the entire thing is neutral, but it is made up of some nuclei and electrons. So what this theory says, at some electrical field, if it is coming closer to this, then there can be some fluctuation. Maybe the positive part of the another thing might pull the electrons on another side. Okay, this like you have to little bit theorize and you have to consider that one part is shifting to some side, but this is also like a temporary thing. So this temporary effect we are going to call as some kind of polarization. Okay, creation of some temporary or induced dipole moment. With this kind of induced dipole is there. So and if another molecule like this is like a which is a non-polar molecule, this particular thing, if you see it again, it is not having any of the developed charges, but something, some polar molecule like water is coming closer to that molecule. Okay, so then you can see temporarily positive and negative changes are happening. So this can be also considered as some kind of van der Waals interaction, but these are weaker compared to your earlier dipole-dipole interaction. But still, these kind of interactions are also very important. Like next semester, we'll talk about our course energy and environment. There we will be talking about some of these structures called as clathrate hydrates. Anybody has any idea about what are these structures? Clathrate hydrate. Okay. These are one of the most important energy related thing. Now you know all your coal, petroleum and natural gas. So something you can consider this is related with your natural gas only. But these are like hydrates in the form of, these are also called as methane hydrates. So methane is something non-polar and water is something polar. How the two things stay together. Generally we know polar liquid mixes well in polar liquid, right? Like methanol mixes well in water, or non-polar things are, they will mix with non-polar things very properly, like the benzene will mix with maybe things like THA properly because both of them non-polar, but normally polar and non-polar things do not mix well. So how these kind of things actually stay together, and this is actually clathrate hydrates is one of the very good research area where actually people know that within the ice actually you have so much amount of energy trapped, and the energy is trapped in the form of these clathrate compounds, which are nothing but the loosely bound compounds, loosely bound between what non-polar and polar molecule. Non-polar molecules are methane or some other lighter hydrocarbons like ethane, and polar is water. So how these two things are interacting with each other? So they are interacting together with these kind of dipole induced dipole interaction. Okay, then there can be third kind, even like non-polar, two non-polar things like methane, take example, will be interacting with another methane molecule. I said how the two methane molecule, like how two oil-like molecules, they will be staying together, even though both of them are having net dipole moment are as zero. So here also this concept can be considered as again theorized. They say there is another source of attraction that does not depend on the existence of permanent dipole moments like you have in the water molecule. But even though the compound are totally non-polar, still it can be considered, if you want to talk about interaction, again something positive and negative should come into picture. But we know that non-polar molecules do not have any dipole moment. So theoretically, it has been observed that when we are talking about the dipole moment also, we are talking about the time average dipole moment. The time average dipole moment is zero, but if you talk at a very short time scale, the electrons must be also localized. Like if you talk about any one particular atom, so you can say there can be temporary fluctuations on their own also. So where the electrons can come on the one side and the nuclei can be on the another side. In the same way, some kind of dipole moment, this will be at a very short time scale. And again, the positive part of one thing will be interacting with the negative part of another thing. So these should be considered as the weakest kind of van der Waals interactions, and these are called as London dispersion forces. So if you summarize these three things, you can consider between water, there are dipole-dipole interaction, which are also called as polar-polar interactions. Especially they have names as Kizom interaction. Between the polar and non-polar, water and methane, there are these kind of Debye forces. And the third one, the weakest one, are the London dispersion forces, but still they are important because if you try to calculate and match with the actual experimental energy without incorporating these things, the values will not be satisfied. So they know there are some kind of unknown things, and this has been theorized like this. Okay, this should be considered between the two methane molecules or between the two CO2 molecules. Now we have talked about all these interactions and we want to incorporate these things into our force field. So actually in our force field, what we talk about the traditional force field, what formula I have shown to you, there actually anything like charges or something do not change. With time I said force fields are actually developing. So still we want to incorporate these kind of effects. If the methane is coming into contact with methane or methane is coming in contact with water, so we have to do certain things to take care of these kind of interactions. So along with the, I said, not always like the Qi and Qj value what we took into consideration in the electrostatic interaction, they are also about some of the atomic charges. These are not the molecular charges, atomic charges. So they take care of the electrostatic interaction. But still there is one more thing in van der Waals interaction, we have some factor called as epsilon. This epsilon will actually take care of how the two molecules are going to be interacting with each other with what particular strength. Okay, so these how to incorporate the van der Waals interactions in our force field formula, this we can talk about. So the formula you have seen earlier that was somewhat related with the this P is nothing but here your U only. So U of R, again this R is nothing but your R of I and J. The interaction, the potential energy between the of interaction between the two atoms, and this is going to be shown by this particular formula 4 epsilon sigma by r power 12 and then again sigma by r power 6. Now this is just one of the formula. Again, different force field might be using different formula for evaluating the van der Waals interaction. This particular formula it is called as Lennard-Jones potential. Now this is actually people use because I said which terms are difficult to evaluate computationally, the bonded energy terms or the non-bonded energy terms. Okay, I explained to you that non-bonded energy terms are the most difficult things to be evaluated because here, even if you consider molecules like this, which is like pentane kind of molecule, you can consider if you want to evaluate bonded energy terms, one, two, three, four. Four things have to be evaluated. But for same molecules, if you consider non-bond interactions, so first atom has to interact with the second, third, fourth, fifth. Second molecule has to interact with 1, 3, 4, fifth, again something like this. So proportional to 4 calculation, you can see how many calculations are coming into picture. So of course the non-bonded interactions are more computationally intensive. So again, if you want to do this considering your current computational theme, it is going to take very time consuming. So people actually use again some approximation, but still they want to be as closer as possible. So there are different variations of this formula, but this particular formula has been designed in such a way that sigma power r, it is raised to the power 12, and this is sigma power r raised to the power 6. So this is called as also 612 potential. Like simply if your computer is calculating sigma by r power 6, simply if you take square of that, so this term also will be evaluated very easily. So computationally it becomes faster. That's why so many of the programs, if you see, they will be inherently, they will be using something called as this LJ or 612 potential. Now I said we want to evaluate these things correctly, and if you want, again here also the force field. So force field potential energy is the function of what? Conformation or the structure. So something, there is a variation in the structural aspect. Now here structural aspect is not something about bonded or something, but about how the arrangement is happening, how the two molecules are being present away from each other. Somewhere there is variation in the position, that is according to the potential energy is changing. And this, there are two parameters. These are the variable, but there are the parameters. Parameters are sigma and epsilon. So for any molecule, if you know only these two things, sigma and epsilon, so at whatever distance they are, accordingly you can calculate their van der Waals energy for any molecule in the world. If you know only sigma and epsilon, only two parameters, you can calculate the van der Waals energy between them for any distance. So this is, I said, a very simplified formula. So what is the sigma and epsilon? So epsilon, if you see, it is called as well depth, and well depth, why well depth? Now I can draw. Always you have seen things like this. The electrostatic interaction was different. It was either like this or it was like this. Okay. Now here actually you have multiple features. It is not simply attractive and repulsive, not just attractive and repulsive, but something like a combination of two things. Okay. You can see it has been shown some attractive part is there beyond this particular line, and there is a repulsive part beyond this line. Okay. So if you see always the van der Waals interaction, you will see the plots like this. Okay. So this, I have talked about this kind of plots. This is on the y-axis. You again have the potential energy, and this is the distance. Okay. So there are some features. So based on these features, only these sigma and epsilon parameters have came into existence. So if you again see for longer distance, longer range, so the potential energy value, it will be zero. There the potential energy change is zero. There is no interaction between the two things. But as the two things are coming together after certain distance, there will be a pull, like the two things will be attracted towards each other, and they will come at some equilibrium position. And then again, if they try to come closer, so there will be some repulsive forces that will come into picture. Okay. So based on, if you see, there are two things actually that needs to be considered, which are related to this epsilon and sigma. One feature is this depth. So this is depth. This is called as some kind of well. So this well is there, and then it is having some depth. So based on what is this depth, this you can consider in terms of some energy. So this energy will be talking about what is the depth based on how strongly the two particles, this particle I, if I talk at the center, and this is the particle J, so how strongly they are interacting with each other. So you can consider more the epsilon value is there, more strongly the two particles are going to attract each other. Okay, so this one thing we have taken care. But along with that, there is another important feature. It is the so if you try to visualize this thing compared to this graph, so this is the epsilon. It has been mentioned here from this point to this point. This is the epsilon value talking about the strength of the interaction between two particles. There is another feature. This is called as sigma. The sigma is what? It is the distance at which intermolecular potential between two particles is zero. Okay. Here you can see some distance is there where actually the two things, both the repulsion, if you talk about if it is positive, then it is repulsion. If it is negative, then it is attraction. So at this point, both the things are getting balanced out. So balanced out means you can say this particular point where it will get balanced out. This particular distance for particle I to particle here J, this distance will be called as sigma. So what is this sigma value? This is actually different for every different particle. It will be related with the molecular sizes. Like I said, each atom is going to have its van der Waal radius, right? The carbon atom, I said, it is having some van der Waal radius of around 170 picometer. So you can consider the another particle, it will not be able to pass through this particular distance. So this particular distance from the center of one thing, if you want to talk about here, so the entire thing you can call as the sigma, or it is also called as the van der Waal diameter. If you want to talk from center to the another center of another particle, this can be also called as sigma. So this will be van der Waal diameter. Either you call for the entire thing or between the 2 points. So this sigma is nothing but you can call it as van der Waal radius. At different sources, people sometimes confuse it with the radius or other things. But just know sigma is nothing but van der Waal diameter, and it gives you measurement of how the two particles can come together. So one parameter epsilon, it is talking about strength of interaction, and another parameter sigma, it is talking about the size of the particle, like how the two things, how closely they can come. So indirectly they are talking about the sizes. So if you define only the sigma and epsilon parameter, you will get van der Waals interaction between them at any distance r. Okay. Now, if you see this particular plot, you can see another thing. There is another distance. Okay, the sigma was something where actually both the things are balancing out each other, but there is another distance which is Rm. This Rm is the distance actually where this well depth occurs. Okay, this is slightly bigger than your sigma value. If you try to find out the relation between sigma and Rm, theoretically you can see it is somewhat related to forgot the exact, but it is 1.12 sigma power uh, sigma power 1 by yeah, I think it's on. So this 1.12, it is actually resembling 2 power 1 by 6. 2 power 1 6 times sigma 2 power 1 by 6 is 1.12. This kind of relations are also there. Different softwares, I said different parameters they incorporate. Some softwares define the value of sigma, certain softwares define the value of the Rm. So, like if somebody is going at the deeper level, so if they do not know the relation between the two, it gets confusing. So you can say what is this Rm distance? What is the difference in sigma and epsilon? Sigma and Rm. Rm is the distance at which intermolecular potential reaches its minimum value. This was the position where both of the things were balancing out each other properly. But this is the position actually where attraction is dominating the most. Like at this position, you should actually assume this particular thing. Like this is the maximum distance at which like the equilibrium takes place. At the equilibrium, some space will be there between the two. But if you try to pull them even more closer, so after certain time, you cannot cross the boundary. So actually this sigma, whatever if you think, this is not actually this particular thing, but you have to take into consideration like this. This is the position like the radius of one particle like this and the radius of another particle. So this is will be sigma value. But if you want to talk about the equilibrium position, at the equilibrium position, both of the things will stay slightly away from each other. So when you want to represent at the equilibrium position, some slight difference will be there as per how this model works out. So if you want to understand this, what are these 12 and 6 term? I said if anything you know about any of the particle about their sigma and epsilon thing, you can estimate their van der Waals interaction. And if you closely look for this van der Waals interaction, there are two terms. One is the repulsive term and other is the attractive term. So if you see attractive term, this is shown like this. This is actually, if you mathematically want to represent this separately, the attractive term, it can be represented as minus 1 by r power 6. This is like somewhat more flattened kind of curve, whereas this is some kind of steep curve. The repulsive curve is uh, uh, plus 1 by r power 12. Okay, so this is higher power, you can consider this is more steeper, but it is positive. This is indicating the repulsion, and the overall Lennard-Jones potential, it is actually made up of that both things by addition of both attraction and repulsive term. Okay, so if you see this, what is the basis of the attractive term? This you already know. We have talked about all the different a kind of interaction that could be possible between the polar-polar, polar non-polar, or non-polar non-polar. So these are the basis for this attractive long-range term, which is normally, actually most of the time when people talk about van der Waals thing, they will be always talking about the attraction only. There is nothing in van der Waals thing like the repulsion forces. But if you want to define the van der Waals interaction together after a particular point, then actually it becomes meaningless because the repulsive forces start, but this also you need to take into consideration. So these repulsive forces, there is no such some actual way you can define it, but this comes from a theory called as Pauli's repulsion. If you go at the electronic level in the quantum mechanics, there will be a theory Pauli's repulsion. This will be related with the overlapping of electron orbitals, and accordingly, this term, the repulsive term, comes into existence. So this is actually given by positive, and when you add both the positive and negative terms, so then you get this your van der Waals interaction term. So whatever is the magnitude, like magnitude of the repulsive and attraction term, it is actually dependent on your sigma and epsilon value. So many times the same formula, what I'm saying as 612 potential or LJ potential, it is also so many times we'll be calling as AB potential. So in the A and B form, this will be represented as, and again I said, for estimating any van der Waals interaction, you always need to know only two things, epsilon and sigma. So this A and B are nothing but they are derived from epsilon and sigma only. If you try to um, substitute the values of this epsilon and sigma into this particular formula. So accordingly, it will be resultant into this AB form, B by R power 12 and minus A by R power 6. So this minus term, it is because of the attractive thing. Okay. So to understand these concepts totally, I have a detailed numerical problem where so many concepts related to not just energy but also related to this equilibrium. The force also comes into existence. So you can understand at molecular level exactly how the things of potential energy forces they takes place. So we will take example of just one of the molecular case, like we will take example of some parameters like a, and it will having some a and b value. This can be either again represented in terms of simply epsilon and sigma, and we will try to understand all these detailed things, how exactly the values could be evaluated at different distances. Okay, any question here? uh, Anything you want to ask related to mini project? Okay, so I said next Monday again I will take my regular class, but next Wednesday and Friday we will have presentations. So I already took the name Pavani, Prabhupada, Tanmay, Rashmi, Pranit. Their group should be ready by Wednesday. Any of the 2, 3 groups I will ask to talk on Wednesday, and the remaining ones on Friday. So I think we can add one more group here. Vignesh, your group also, please be ready. Try to be ready by Wednesday. If there are any problems coming, we'll try to figure it out. But some of them, most probably on Wednesday, Rashmi, your group, Prabhupada, your group, and Tanmay, you also. Okay, with 3 groups, try to be ready. If there are issues, we'll discuss and figure it out. Okay, I know you guys have other things also. Accordingly, we try to tune our this mini project presentations and calculation. Okay, those who are having any individual problems, no, I said I will talk with them individually with next time.
Sir, I had a question regarding this template.
Yes, Nikita, what is the question?
Describe attraction at low ranges, but van der Waals forces are short range forces. So I didn't get what they mean by long range.
Nikita, your voice is breaking in between. You said exactly what?
Hello.
Yes.
So it's written here that this describes long
Attractive
ranges. I didn't get what they mean by long ranges.
long range forces.
Yes, sir, because the van der Waals are usually short range forces. So
Mhm. Yes, good question. Actually, now this distances matters in terms of what actually distances you are considering. Means when it is talking about long range means something like here. Okay, not when we are talking about the shorter range, you can see the magnitude of the things still here only. But if you see, so many times I said things are theorized and it has to be theorized properly. So even up to some distance, it just stay. It doesn't come zero directly. Like here, maybe in this graph, you are saying, okay, it has came to zero, but it will take a very long time. Till long distance, you can see it will take time to become zero. So what is the basis of those long range interactions? So that's why I explained to you those kind of very weaker interaction, right? There are those again non-polar interaction will be also there, no? So many times they will be calling it as long range interactions. And when you are taking at a very short distances, they most of the time they are your regular van der Waals interaction what to talk about. You can say this doesn't flat out very quickly. It will be taking time. So those basically uh, they are talking about this long range thing. The dispersion force. If you go into details of London dispersion forces, no, you will understand what happens.
okay, sir.
Excuse me, sir.
Yes.
So while performing the molecular modeling, the value of DE all of a sudden increases. Like initially it's decreasing, and I've noticed that as it approaches the value of zero, at some instances the value increases all of a sudden. So why is that happening, sir?
Pawnee, between what and what you are trying to evaluate?
Sir, I was trying to model the structure of insulin on the on avocado.
Okay, so insulin, you are having one molecule and the other thing.
Sir, for now, I have just tried to model it individually, sir.
Then D value based on what you are saying. How
Sir,
will it change?
force field is GFF, sir.
Yes, but you are saying DE value. So when you are talking about DE value, it is related to when two things are coming together, or it is related with the only the energy minimization you are doing.
Only energy minimization, sir.
So in energy minimization, if you take any structure randomly, initially its energy should be high, and when you do the geometry optimization or energy minimization, then the value should be lower. So DE value will be always it will be lowering down only, negative only. So you are saying it is increasing again.
Yes, sir. Like as it's approaching, initially it had started in range of 100 or no, it was more than that. And as it was approaching zero, all of a sudden, at certain instances, the value was incrementing to 2.4, 2.6, 4, and again it was going down to zero. It was not decreasing monotonously towards zero.
I should say that it should decrease only. I have to look for your problem. It should, when energy minimization happens, it just decreases.
Okay, sir.
I will discuss it too.
And sir, one more doubt, sir, in the software there's an option of decreasing the speed, increasing the steps per update. There's an option of steps per update in the software. So
Yes.
on when we googled it, the website says that if the computer is processing it very slow, then we should decrease the steps per update.
Okay.
But is